Hello, this is Jack Jackson back again, and we're going to continue our investigation of congruence of triangles in different conditions. In the last video, we looked at the ASA condition in Euclidean geometry. We're going to do the same thing in hyperbolic geometry. So once again, I'm going to go to my geometry collected resources where I have lots and lots of um, applets created in GeoGebra. Um, and then also that I've created, but also some that other educators have created. So here we want to look at the hyperbolic triangles in hyperbolic geometry. And here we can see that we have the investigations for all the different ones. We've looked earlier at SAS. Let's look now at ASA. It's best if you take this and open it in the app like that. And so we have uh, a situation here. So what do we have? A point, free point that we can put anywhere. And we're given first an angle. So remember, hyperbolic angles look like this. These are hyperbolic rays, part of Euclidean circles, that they go from the vertex down to the edge, which is the x-axis. And then we have, if we finish a full circle, the center of this circle would be on the axis in the first quadrant here, or above the x-axis anyway, would be a semicircle. So anyway, that's an angle as we've looked at earlier. So we take that angle. So we started with the first angle here. Now we're going to go out this side. So that means we construct a circle of that radius, and we can go anywhere on that circle and move where this works. This may break a little bit in cases it should mostly work. Okay, so there we go. There we have an angle, and you can see its measure there is what we put here. We can adjust the size of the angle, and we can adjust the size of the circle. Okay, next we go out an angle on the other side, like that, at the other end at angle B. And you notice that these two rays here, the point C, the other vertex, has to be on this ray, because it's got to make this angle A the right size, and the angle at B has to be the right size, so it also has to be on this ray, and they only intersect in exactly one point, and that's enough to make exactly one triangle. It's exactly the same situation that we had really in Euclidean geometry. It works out, uh, and no matter where we do this, these triangles are staying congruent. Now, they may not look congruent. They're not congruent as Euclidean figures, uh, but using the distance metric that and the angle measure and so forth that we have in hyperbolic geometry, these are staying congruent triangles. Okay, and we can see all those measurements. See, they stay the same no matter where we put those. We're using the actual measurement tools that I built into GeoGebra. Okay, now you can break this one in the same way that you can break the Euclidean situation. You can make a no solution case. If you make the angles too big, I'm not sure I can even, if this is even being illustrated correctly. Uh, it's not really illustrating very well. But if you have if the angles, you have the same situation you have in Euclidean geometry. If you have the angle is too big, uh, then it turns out to be impossible to make a triangle. It's exactly the same condition. The angles in a Euclidean triangle, the interior angles, their measures add up to pi radians or 180 degrees. In hyperbolic geometry, they add up to less than pi radians or 180 degrees. So if you get these two angles here to have measures that add up to pi or more, then if their measures add up to pi or more, then in fact no such triangle is possible. So we see that in the hyperbolic geometry case, given any measurements that you have, you're either going to have no triangle possible, zero congruence classes, or if the triangle is possible, if these two angles measures add up to less than pi, then there always is a triangle possible and they're all congruent. So there's a one triangle congruence case there. So it's either zero congruence classes or one congruence class. And we see that if we have two triangles with these matching conditions of angle, side, angle, matching sides, corresponding sides congruent, then that's enough to make the triangles congruent. We have exactly the same conclusion that we had for Euclidean geometry.